This video's sponsor is Squarespace, a revolutionary web building tool. Wait, really? We'll see. It's 1887, and Heinrich Hertz is about to make history. He turns out his primary coil, producing a very strong spark over here, and almost immediately, a second spark appears in his handheld coil. Electricity had jumped through the air. He had demonstrated for the very first time the existence of electromagnetic waves, one of the core predictions of Maxwell's equations. But little did he know that soon he would stumble upon something totally by accident that would shake the very foundations of physics. See, while playing with these sparks, he noticed something, almost by accident, that shining ultraviolet light on the metal made the spark length bigger. He had no clue what was going on, but he probably didn't care much because he was celebrating the discovery of electromagnetic waves and was probably too busy having a unit named after him. But soon, the electrons were discovered, and it then became clear what was going on. The ultraviolet light ejected electrons from the metal. This made the spark bigger, and it was called the photoelectric effect. And this led Einstein to revolutionize our understanding of light, eventually earning him the Nobel Prize. Right? Well, when I first learned about the photoelectric effect, I was wondering what the big deal was. Why did Einstein win a Nobel Prize for explaining it? I mean, I can explain it. See, light has energy, and that energy is absorbed by the electrons, and the electrons use that energy to escape from the nucleus, giving you photoelectric effect. There you have it. Where's my Nobel Prize? And more importantly, it's said that this effect led Einstein to develop his theory of photons. But how exactly? And was it really Einstein who developed the idea of photons? Wasn't it this guy? Max Carl Ernst Ludwig Planck, who came up with this idea while studying the black body radiation. I mean, E is equal to h nu or hf literally has Planck's constant in it. So why do we credit Einstein for the discovery of photons? None of this made any sense. That is, until I dug into the details of all the history and all the experiments that went behind it. Then my mind was truly blown. So if I do this right, then by the end of this video, we would have rediscovered step by step all the thought processes and scientific models that slowly and steadily evolved, which led to the quantum revolution of light. So if you're ready for this, let's begin. Einstein says, Mahesh, you're absolutely right. Initially, even we thought, what's the big deal with the photoelectric effect, right? That is until a man named Philipp Lenard, who was Heinrich Hertz's assistant, made a shocking discovery. What was the discovery, Einstein? Einstein asks, Mahesh, if you were to increase the intensity of light over here, what do you think will happen to the speed at which the electrons are coming out? And I'm like, well, if you were to increase the light's intensity, then you're pumping in more energy, electrons are going to absorb more energy, so they will come out with more kinetic energy. They'll come out faster, obviously. And that's exactly what Lenard thought. But Lenard wanted to win a Nobel Prize. He wanted to make his mark in the scientific community. So he says, hey, why don't I experimentally test this? And I'm like, wait a second, how are you going to experimentally measure the speed at which electrons are coming out? I mean, it's the 1900s. Well, Lenard comes up with a brilliant idea. If a baseball is moving very slowly with a little bit of kinetic energy, it takes a little bit of effort, a little bit of energy to stop it. But if that same baseball was moving much faster with more kinetic energy, it takes a lot more energy to stop it. So by figuring out how much energy it takes to stop something, you can estimate its kinetic energy. Okay, so if you could figure out how much energy it takes to stop these electrons, then I can estimate the kinetic energy of these electrons. That makes sense. But how in the world are we going to try and stop the electrons? How would we know how much energy it took to stop the electrons? Lenard's brilliant idea is to use a negative voltage. Think about it. Electrons are coming out from here, right? Now, if we use another metal to collect the electrons, which we're going to call the collector, but put a negative voltage to the collector, then that will repel the electrons and it can make the electrons stop. Now, if it takes a little bit of voltage to make the electrons stop, that means the kinetic energy of the electrons was very little. But if it takes a lot of voltage to make the electrons stop, that means the electrons had much bigger kinetic energy. Makes sense, right? And I'm like, yeah, that makes sense. But how do I know if the electrons have stopped or not? Like, I can't see them, right? This is where you put an ammeter. If the electrons are collected, then there will be a current and the ammeter will detect it. In fact, in this particular example, there is a current. That means I know the electrons have not stopped. So this much voltage is not enough. So let's turn up the voltage until the current just stops. So at this point, I can now visualize that all the electrons that are coming out of here must have stopped and must have turned around. None of them are getting collected. So in this case, it takes 3 volts to stop these electrons, right? Now imagine another photoelectric experiment in which it took, say, 6 volts to stop the electrons. Then I can immediately compare and say that, hey, there, the electrons must have come out with more kinetic energy. In fact, about twice as much kinetic energy as over here, because it took twice as much voltage to stop it. This means this stopping voltage, as we call it, is a direct indicator of the kinetic energies with which the electrons are coming out. And looking at this, I'm like, bravo, Lenard, bravo. That's truly brilliant. So what was the shocking discovery? What did you find? All right, now Mahesh, what do you think should happen to the stopping voltage as you increase the intensity of light? And I'm like, as we increase the intensity of light, since electrons will come out with more kinetic energy, it should be harder to stop them. The stopping voltage should increase. Exactly. But when Lenard did the experiment, what he found is that increasing the intensity of light had no effect on the stopping voltage. The stopping voltage did not change at all, regardless of how bright he made the light. I mean, of course, we're dealing with UV light. You can't really see it. He was using a lot of filters to change its brightness and change its intensity. But you get the point. Increasing the intensity has no effect on the stopping voltage. And the big question was, why? How does it make any sense? I'm pumping in more energy, and yet electrons are not coming out with more energy. How does that make any sense? Now, of course, Lenard did find that increasing the intensity increased the number of electrons that were ejected. And that kind of probably makes sense, right? Like you shine more light and you'll get more electrons. So that's fine. But the big question was, why weren't they coming out with more energies? The stopping voltage did not change at all. So why is it that if I input more energy, for some reason electrons don't come out with more energy? I get more electrons, but they pretty much come out with the same energy as before. Why is the intensity has no effect on the kinetic energies of the electrons was a big question mark. So Einstein, this is where you come in, right? And Einstein says no. In fact, Lenard actually came up with a brilliant explanation for this as well. Lenard says, Mahesh, think about a cannon. If you light it on fire, does the size of the fire, whether small or big, decide how fast the cannonball flies out? I'm like, of course not. It depends upon the gunpowder and stuff over here. Lenard says exactly. The fire just triggers the explosion. It doesn't transfer energy into the cannonball. And that's why the speed of the cannonball has nothing to do with this fire. It depends upon the gunpowder and all the properties of the cannon. In a similar way, maybe light is only triggering the electrons. Maybe light doesn't really transfer the energies into the electrons. Maybe the electrons already had these energies to begin with while being inside the metal, maybe in some other form. Maybe light only triggers it. That would explain why light's intensity has no effect on the kinetic energy of the electrons. The kinetic energy of the electrons must be an intrinsic property of the metal itself, not the light. Having more light now, it's kind of like having more fire. You can trigger more cannonballs. Similarly, if you have more light over here, you'll trigger more electrons, and that's why more electrons come out. But again, their energies would have nothing to do with the light itself. Looking at this, I'm like, bravo, Lenard, bravo again. And I absolutely love it because we get to see how science progresses. You come up with ingenious experiments and then come up with hypotheses to explain it. This, by the way, was called the trigger hypothesis. And I have absolutely no idea that it existed. My books didn't cover this. But anyways, Lenard wanted to be absolutely sure about his hypothesis, so he conducted even more experiments. And soon, he found his trigger hypothesis to be in trouble. This time, Lenard experimented with different colors or different frequencies of light. Higher frequencies like X-rays and even lower frequencies like visible light. Now, according to the trigger hypothesis, light is only triggering the electrons. So the energies with which electrons come out should only depend on the metal, right? So this means the frequency should have no effect on the kinetic energies of the electrons, right? But what Lenard found was that was not true. Lenard found that the high frequency light actually made the electrons come out with more kinetic energy, and lower frequency light made them come out with lesser kinetic energy. And if light's frequency was too low, then electrons didn't come out at all, no matter how bright you made the light. This means the electron's energy not only depends on the metal, but it also depends on the light. Not its intensity, but its frequency. Higher the frequency, more kinetic energy. So it's doing more than just triggering the electrons. The trigger hypothesis was in trouble. Lenard was in trouble. He tried his best, but now we really needed to bring out the big stuff. We needed a revolution. Kind of like the revolution that we had recently when it comes to building websites, which is Squarespace, the sponsor of this video. Okay, seriously, why do I call it revolutionary? Here's why. If you want to create a website, you start by just clicking this button which says create website. Can it be any clearer? Then it gives us two options. Now, if you're a beginner like me who has no website building experience, then you can choose the templates. There are a lot to choose from, so I chose portfolio, picked the one that I liked, edited things by clicking buttons. They're hyper customizable, and in a few hours, FloatHeadPhysics.com was live. Actually, no, it didn't. I got stuck in between. Some weird problem came up. But there was on-demand support. I kid you not, this really happened. And within minutes, the problem got resolved, and now finally, the site was live. Now, I know what you're thinking. Mahesh, not everyone's an amateur like you. What if I'm a professional website builder? Well, then you choose the other option. Because this one lets you build everything from scratch. You can decide exactly how all your pages should look like, the colors, the fonts, and then you can edit it to perfection. And then once it's live, there are also advanced analytics tools to give you feedback on a ton of stuff. But what's really awesome is you can get started for free and immediately create a digital presence, which I think everyone should. So if you want to get started for free, just go to squarespace.com/FloatHeadPhysics. And of course, if you decide to make a purchase, you can even save 10% by using the promo code FloatHeadPhysics at the checkout. Okay, happy website building. Now back to the video. This is where Einstein comes in. So Einstein, what went through your mind when you went through the results of the photoelectric effect? And Einstein says, nothing initially. But luckily, a few years ago, he had gone through another paper by Max Planck on the black body radiation. Connecting the dots from that experiment and this one inspired him to come up with something truly revolutionary. But what is it? What did he find? Well, the details of the black body radiation and how Planck solved it is a story for another video. It's also very interesting, so let me know. But for the purpose of this video, to understand how it inspired Einstein, we don't need to get into the details. We can use a brilliant analogy to get the essence of what happened, okay? Light's energy is like this water, smooth and continuous. You can transfer any amount from one cup to another. Like you can transfer 1 ml or 2.3675 ml, whatever you want, right? But when we treated light like this, where you can transfer any amount of energy from one object to another, our theories couldn't explain the experimental results. Again, the details of that experiment is not really important, but what's important is that try as you may, if you allow water to continuously be transferred from one cup to another, you cannot explain the experimental results. So when finally Planck stumbled upon this, he too struggled to fit the experiments just like all the other physicists did. And so in later what he called an act of despair, he came up with a wild idea. Instead of a continuous transfer, what if you could only transfer water in specific amounts, like a minimum of 1 spoon? So you can transfer 1 spoon or 2 spoons worth or any multiples of spoons worth of water, but not say 3.5 spoons of water, for example. And immediately I'm like, Planck, why would you do that? Well, Planck says it's a counting trick. Okay, if you allow the water to transfer continuously, I cannot count it. But if I do it 1 spoon at a time, now I can count how many spoons of water has transferred. And in fact, and you can literally see it in this paper that he's using it as a counting trick. But wait a second, Planck, how big should that spoon be? Planck says, this is where he realized if the spoon size depended on the color of the water. So if you have high frequency water, you have bigger spoon size, and low frequency water meaning smaller spoon size, then he could probably explain the experimental results. So he comes up with this random condition that the minimum quantity of water that you can transfer, the quanta, the size of the quanta, should be proportional to the frequency of the water, frequency of light. And again, remember, he's only doing this to fit the experimental results. It has no physical reason whatsoever. And I'm like, Planck, what's the point? Even if you're successful in explaining the experiments, how will you explain why this is true? Why you have to transfer some minimum amount, and that minimum amount, that minimum quantity depends on the frequency of water? Well, you have to give some explanation, right? And Planck says he doesn't have to. This is where his final step, his masterstroke comes in. Planck says if this all works out, if he can explain the experimental results, then he will just set his proportionality constant to be 0, which means in reality, there is no minimum quanta. There are no spoons. It was all a counting trick after all. Water is just continuous and he doesn't have to explain anything. Bravo, Planck, bravo. Did you like the analogy? I mean, I loved it because it captured the essence of what Planck was trying to do without having to get into the details of the black body radiation and all of that. But now the big question is, did it work? And Planck says it half worked. His strategy worked perfectly and he was able to perfectly explain the experimental results. Yay! But he wasn't able to get rid of his constant. He found out to make all of this work, that constant had to have a particular value. And that value is this. Yes, very close to the Planck's constant accepted value that we have today. But think about what this means. This meant that it was no longer just a counting trick. It was physical reality, that nature is indeed transferring water in some minimum quantas. But Planck hated this idea. That was never his intention. He never wanted to quantize anything. If water is continuous, why is nature forcing you to, restricting you to transfer it one spoon at a time in a multiples of a particular spoon size? Why was nature doing that? It just didn't make any sense to him. This is where Einstein jumps in, and let's look at how he connects the dots now. Planck's energy quantas depend on the frequency. And now, even in photoelectric effect, we again find electrons' kinetic energy also depends on frequency. Can this be a coincidence? He thought no. So he came up with a much cooler idea. What if light is not like water at all, but instead like ice cubes? Then we don't have any choice but to transfer one cube or two cubes or in multiples of one single ice cube. So here's the difference between how Planck and Einstein thought. According to Planck, light is like water, smooth and continuous. But for some reason, nature only transferred it in discrete quantas. It didn't make any sense to him. Why would nature do that? He didn't believe in quantum anything. In fact, he was so anti-quantum, he didn't even believe in atoms. But it was Einstein who took it to a whole new level. Einstein says, buddy, I can give you a reason for why nature might be doing that. What if light is not like water, smooth and continuous? What if light itself is made of these discrete quantas, like ice cubes? Then she has no choice but to transfer one cube at a time. So look, Einstein gave a physical interpretation of what Planck had discovered when he was trying to do his math counting trick. And these discrete chunks of light is what Einstein called the photons. So you can clearly see it was Einstein who came up with this revolutionary idea of photons and not Planck. Bravo, Einstein, bravo, truly out of the box thinking. But the big question now is, can this explain the photoelectric effect better than the trigger hypothesis? Let's find out. According to Einstein, light is not made of waves, instead of particles like ice cubes. And he says when you shine light on metals, the electrons have to absorb one entire quanta, the entire photon. You cannot absorb half of it, okay? So what happens now if electron absorbs the entire photon? Now, if the photon doesn't have enough energy to kick that electron out, well, then the electron will just re-emit that photon back. And now even if it absorbs another photon like this, again, it will re-emit it back. So look, if you're shining light whose photon energies are too small to kick that electron out, you will not get photoelectric effect. And if you were to increase the intensity of light, what you're really doing is just increasing the number of photons. But since a single photon doesn't have enough energy to kick it out, regardless of how many photons you shine on it, nothing's going to happen. It's kind of like trying to knock over this golf ball using mosquitoes. It doesn't matter how many mosquitoes you throw at it, that golf ball is not going anywhere. But of course, one question we could ask Einstein is, why can't an electron absorb multiple photons at the same time and then gain enough energy to escape it? And Einstein says, I don't know. He didn't have an answer for that. But today we do. See, photons and electrons are quantum objects, incredibly tiny particles. So the chances of an electron absorbing two photons at the same time, that is incredibly, incredibly small. So it can happen if you have insanely high number of photons, incident per second, and that can only happen at very large intensities of light. And we have seen multiphoton absorptions in such large intensity lights. But as long as the intensity is not so freakishly high, then the probability of that happening is just too small. So this means for photoelectric effect, a single photon should have a minimum amount of energy to kick the electron out. And since the energy of a photon depends on its frequency, that's the reason why you need a minimum frequency for photoelectric effect to happen. If the frequency is too low, the photon energies become too low and the electrons won't get kicked out. And now as you increase the frequency, the energy of the photon becomes high enough that it can kick out an electron. And now if you further increase the frequency, then the energy of a single photon becomes even more. So when the electron absorbs, it gets even more energy, and that's why it'll come out with even more kinetic energy. This now perfectly explains why, as the frequency increases, since the photon's energy increases, it transfers more energy to the electron, and that's why the kinetic energy will increase. That's why the kinetic energy, or the stopping voltage, depends on the frequency of light. And of course, if you were to increase the intensity, what does it do? Well, it just increases the number of photons. So that won't affect the energy transfer to a single electron. But now, since there are more photons, more electrons will be emitted. And that explains why increasing the intensity gives you more electrons. The photon theory beautifully explains the photoelectric effect. Einstein, take a bow. Your theory must have been now accepted in the scientific community super easily with barely any inconvenience, right? And Einstein says, actually, no, Mahesh, it was really hard. In fact, even for more than a decade, people didn't believe in the photon theory. And I'm like, what? How does that make any sense? This theory explains the photoelectric effect way better than trigger hypothesis ever did. What's going on? There were many hurdles. First of all, it challenged the already established wave model of light. We have century worth of experiments confirming that light is a wave, like interference and diffraction and so much more. And now this patent clerk comes out of nowhere and says that, hey, all of that is wrong and light is not a wave, it's made of particles, and you expect people to accept that? No ways. In fact, this idea was so revolutionary, and people hated it so much that people actually thought that this was Einstein's biggest blunder. I mean, take a look at this recommendation letter written by Max Planck in 1913. You can pause and read this. So he praises Einstein over here, and then he says that he may sometimes have missed the target of his speculations, as for example, in his hypothesis of light quanta cannot really be held against him. Oh man, this aged well. But secondly, the photon theory challenged a Nobel laureate. Who are we talking about? Lenard! That's right, Lenard actually won a Nobel Prize in 1905, the same year Einstein published all his beautiful papers on special relativity and photoelectric effect and Brownian motion and all of that. And Lenard won it not for photoelectric effect, he won it for his contributions to discovery of electrons. He did a lot of work over there. But anyways, with the Nobel Prize came a huge ego. So a mere patent clerk had dared to challenge a Nobel laureate? That triggered Lenard. So he became a full-blown anti-quantum, anti-relativist, anti-Jews, and anti-Einstein. And he had a huge influence on the scientific community. So Einstein, this is really bad. Who came to your rescue then? Now enters our final character, Robert Millikan, a huge experimental physicist. And I'm like, that's the guy who discovered the charge of an electron using the oil drop experiment. Was he in the favor of your theory? And Einstein says, no, he was in fact one of the biggest critics. And yet he played a crucial role in validating the photon theory, completely unintentionally. Millikan was not only against the photon theory like most other people, but he found something extremely weird in his 1905 photoelectric paper. So weird that he said, Einstein, not only am I against you, but I'm going to experimentally prove it to you that you and your photon theory is absolutely wrong. He was absolutely convinced that it is wrong. But what did Millikan find so weird in his paper? I mean, the photon theory made perfect sense to me. It nicely explained the photoelectric effect. So what was so weird? And Einstein says, Mahesh, yeah, there was something weird in my photoelectric paper. There was a bold claim that it made, and even I was a little nervous about it. What was it? And Einstein says, all right, Mahesh, for this, we need to do a little bit of math. And I'm like, no, not the math. And Einstein says, Mahesh, don't worry about it. The math is going to be super intuitive. If you want, take a break and then come back, because this is it. This is the climax. This is the moment of truth. So if you're ready, let's do it. All right, welcome back. We have a ball and we're going to kick it up, giving it 100 units of energy. Our goal is to figure out how much kinetic energy the ball would have when it comes over here. That's it. That's all we need to figure out. Okay. Now, as the ball goes up, it's going to lose some of that energy to gravity because it's doing work against gravity, isn't it? So let's say that work that it does, the energy that it loses against gravity is 30 units. So how much energy is left over here? Well, 100 minus 30, 70 units. That's the kinetic energy, isn't it? And that's it. That's all there is to it. So we can now write down an equation. The kinetic energy of the ball, when it reaches over here, is going to be the energy which you kicked it, minus the energy that got used up to overcome gravity. Makes sense, right? I'm like, yeah, that makes a lot of sense. Now Einstein says, okay, what if you had a lot of such balls at different heights? Then which of the ball, Mahesh, would have the maximum kinetic energy when it reaches over here? And I'm like, well, it's got to be this one because it's the closest. So it has to do the least amount of work against gravity. And Einstein's like, exactly. So the ball that has to do the least or the minimum amount of work against gravity will end up getting the maximum amount of kinetic energy. Einstein says, Mahesh, this is my photoelectric equation. Of course, I wrote it using different symbols back then, but this is it. This is the photoelectric equation. Because now, if you replace your basketballs with electrons, you get the same idea. If you supply energy of a photon to them, that is E over here, the electrons will use up some of that energy to overcome, not gravity, but electric forces. And then whatever is the remaining energy, that would be the kinetic energy with which they come out. And the electron that is close to the surface is the one that needs to do minimum amount of work to overcome the electric forces. And therefore, it's those electrons will get the maximum kinetic energy. Okay, that looks pretty straightforward to me. What's so weird over here? And Einstein says, Mahesh, let's simplify this a little bit and then you'll get it. Suppose the maximum kinetic energy happened to be 1 electron volt. Mahesh, do you know what it means? And I'm like, I remember studying about electron volts, but I forgot it. Einstein says, don't worry, it's a unit of energy. And 1 electron volt basically means you need 1 volt to stop that electron. That's all it means, okay? So if you apply 1 volt, that electron is going to stop. In other words, the stopping voltage is 1 volt. If that maximum energy of the electron was 3 electron volts, then that means you need 3 volts to stop that electron. In other words, look, if you know the stopping voltage, which you can calculate experimentally, then if you multiply it by E, you will now find the maximum kinetic energy of the electrons that are coming out. I find that fascinating because you can now do big macroscopic experiments to figure out, to measure microscopic quantities. That's how it all works. It's incredible. Anyways, so this means I now know how to find the maximum kinetic energy. Just multiply stopping voltage with E. Now that equals, we know this is the energy of the photon. So energy of the photon is h into F minus this minimum energy needed to overcome the electric forces. And Einstein asks Mahesh, now do you see it? And I'm like, no, what is so weird over here? I can't find out. And Einstein says, all right, don't worry. Let's divide the whole equation by E. That's the final step. So if we do that, if we divide this whole equation by E, we will now get V stop equals HF divided by E minus W minimum divided by E. And look at this, stare at this equation, Einstein says, and I am staring at it. And Einstein says, Mahesh, look, this equation resembles your equation for straight line y equals mx plus c. This means if you were to plot a graph of the stopping voltage versus the frequency for any material for photoelectric experiment, then we should get a straight line which has a slope of this number and the intercept of this number. And what's weird over here is that the slope has Planck's constant in it. Since we already know the value of E, we can now do an experiment, calculate the slope, and figure out the value of Planck's constant. And Robert Millikan is thinking, what are the chances that the value of the Planck's constant, which we get from a photon theory trying to explain photoelectric effect, is the same as the Planck's constant gotten by Max Planck who was trying to do a counting trick? What are the chances of that? There is no chance that is true, and I am going to prove it to you that that's not happening, and that's why this whole thing would be wrong. That's what Robert Millikan was thinking, and if you think from his perspective, yeah, it kind of makes sense. Back then, what are the chances that the value has to be the same? But moreover, since this slope is a universal constant, this means regardless of what material I use, what metal I use, the slope has to be exactly the same. It can have different intercepts, but they should all have the same slopes. And again, Millikan was like, what's the chances of that happening? That's definitely not going to happen. No chance. Okay, he wasn't really evil, but he had a really good point. The claims made by the photoelectric equation was really, really bold, and Millikan just wanted to disprove it. So what happened? Well, for the next few years, he meticulously does this experiment, slowly changing the frequency, calculating the stopping voltage, and drawing that graph. And he does all of that and finally publishes his results. What did he publish? Well, a direct photoelectric determination of Planck's constant. He finds that the slope of the graph of various metals is exactly the same. It's a universal constant. And when he finds the value of h, he finds it to be exactly the same as what Planck found. The writing was on the wall. Einstein and his photon model had won. This is the actual photo of Millikan's writing, and now you can truly appreciate how monumental this piece of paper is. It validated Einstein's theory. This was the final nail in the coffin for the trigger hypothesis. And although World War I started a little bit later and that slowed things down, but it was inevitable. In 1921, Einstein finally won his Nobel Prize, and he got it for the photoelectric effect. Why? Because he found something revolutionary, completely changed the way he thought about light. Now, relativity was also awesome, but nobody understood relativity back then, so it would be much less controversial if you award it for the photoelectric effect. Also, Einstein won this Nobel Prize the next year in 1922. Why? Lenard. Hit that guy. Anyways, this is how a small accidental discovery by Heinrich Hertz catapulted into the discovery of the quantum model by Albert Einstein. But even Einstein probably had no idea what he had done. He had completely shaken physics, because for a long time we thought we knew what light was, and now we're back to square one. Is it a particle? Is it a wave? How do you reconcile all of this together? Sure, today we know about the dual nature of light, but it wasn't such a straightforward jump. What followed over here is a lot of chaos, more confusion, and even more personal battles, but it's even more interesting. I had a lot of fun making this particular video, and I'm super curious to see whether you liked it or not. If you did, oh my god, there is so much I have to share when it comes to quantum revolution, alright? But in the meanwhile, if you haven't already, you can check out my video on Heisenberg's uncertainty principle, which is linked somewhere over here. It's also completely intuitive, and I know you might probably need a break over here, but do check it out when you feel like it. Alright, that's it. See ya.